All right, so we are now recording. So welcome everyone to the second session of the 2021 Developer Conference. I hope you've had a nice break since our fantastic session this morning. And in case you haven't noticed, the videos of this morning's session are now up as a playlist on the ArduPilot.org YouTube channel. So if you were asleep this morning and missed any of the talks, then you can go and watch them. There's a video of the entire session, or there's 4 separate videos of the 4 talks. So you can do it whichever way you prefer. So this evening, we have the pleasure of a talk from Samuel Tabor, who's coming all the way from Scotland and giving us a talk about ArduPilot Soaring. And there's been many exciting things happening in Soaring, so looking forward to it. Over to you, Samuel.
Great stuff. Thanks, Andrew. And hi, everyone. So yes, it's a bit of an update about the Soaring feature, of which I'm the maintainer currently. So a bit of a roadmap to this talk. So although the title is Soaring Update, I realize I haven't actually given a talk about this feature in the past. So to kick it off, there's a bit of an introduction, what it is, why would you want to do it, and a bit of the background about what thermal soaring is all about, and how we can make use of it with UAVs. Then there's a bit of a description about the current implementation in the code, and some recent progress towards improving the existing features. And then the later part of the talk is around some of the new developments which are currently being tested and evaluated. And then finally some future ideas as well. So what is it? So it's a set of features to enable gliders to stay aloft for long periods of time without using batteries or other propulsion, or to do it automatically, ideally. And it's implemented as a library, AP Soaring, and as a flight mode, thermal flight mode. And the history of this technology goes back quite a long way before ArduPilot got involved with it. So it's been under research for quite a long period of time. This is about the mid-2000s by various research groups, including NASA and NRL. I got interested in it about 2013 and developed some of the features as a fork, which I had some fun flying, and then some other people did as well. But it wasn't until around 2017 when that work was picked up by a group under Microsoft, including Ian Gillard here, who's on the call, and they used it in their Frigate Bird project. The link to that is here on this slide. And as part of that project, they dusted it off and rebased it on the current ArduPilot master, and I went as far as getting it pull requested and brought in into master, which was a really great effort by them, as well as being a very interesting project in its own right. And once it was in master, that gave it a bit more visibility, and it got picked up for commercial use in around 2018 by a company, Kraus Aerospace, KH Aerospace, who are now using this commercially, and who I work for, as well as Tom works for them as well. So why would you want to use this set of technologies? Well, first of all, it's very interesting, at least for someone like me, a kind of nerdy engineer. So it really sits as the intersection of a lot of different interesting areas. So you've got the weather, you've got the performance of gliders and of aircraft. You've got a lot of scope for optimization in how the aircraft flies, and you've also got the inspiration of how nature handles it with various soaring birds. So, but as I mentioned, there's also commercial or industrial applications, and one that I've already mentioned is the Kraus and Dani Aerospace K1000 glider, which is a product which is really designed to take advantage of this technology of thermal soaring, as well as having a lot of other interesting features on the aircraft, including high efficiency solar panels and lots of other bells and whistles, like a high bandwidth data link and capable payloads. Now this aircraft, does have very good features for soaring. So it's got a 30:1 glide ratio, and it's got a very long ability to fly due to its high battery capacity and solar power, which means it's a great experimental platform for soaring, as well as being a very useful aircraft for our customers as well. And Craftsman Aerospace is an ArduPilot partner organization. But most importantly, it's a fun thing to experiment with. It doesn't need to be super complicated. I do the majority of the testing on a very simple Volantex foamy in my local flying field, and it's a nice way to get out and enjoy the good weather when it comes along, and enjoy flying your gliders. So a bit of a kind of background to what thermal soaring is, to kind of create a bit of a mental model for the subsequent slides. So it's a bit of a video here showing a kind of time lapse of what happens when thermal soaring conditions exist. So what you have is sunshine heats the air pretty much only right beside the ground. It doesn't heat the air that it passes through on the way down to the ground. And this creates a sort of blanket of warm air beside the ground. And as we know, warm air likes to rise, and eventually this air breaks through the cooler air above it and rises as a bubble or a column of warmer air. And we call this a thermal. And this continues up through the atmosphere until the expanding air, due to the falling pressure, cools down to the ambient temperature, at which point it stops rising. And in a lot of conditions on the way up, the water vapor that it carries from the surface will also condense out, forming these kind of classic cumulus clouds, fair weather cumulus. So here's another kind of visualization. So this is actually from a soaring simulator, Condor 2. And this is the advantage. It also has a sort of cheat mode where it will show you what the air is doing underneath these thermals. So you can see it's kind of sucking up warm air from a fairly wide area. And that's being pulled up into the sky and forming a kind of stream of warm air going up through the atmosphere. And also the wind has the effect of blowing these formations along with it. So if you were to take a slice through the atmosphere on a day like that, with these conditions, you would see something like this plot. This is actually a plot from a LiDAR measuring device pointing up into the atmosphere and measuring the vertical velocities of the air. And you would see that there's these isolated columns of red, which is rising air. And those are surrounded by areas of blue or sinking air. And overall, due to conservation of mass, this the whole thing balances out, so that there's as much air sinking as there is rising. So in order to exploit that, we need to make sure that we spend more time flying our glider in air that's rising rather than air that's falling. And because it's overall average, if we just fly in a straight line and don't make any changes, the effect on the glider will average out. We won't get any net benefit. So there's kind of three groups of techniques we can use to get a net benefit and stay up for longer. So the first one is effectively what's currently implemented in the code, and that's the technique of circling where the air is rising and flying in a straight line through where the air is sinking. And because you're spending then more time in the rising air, you get a net benefit. And there's three sort of components behind how that works currently that I'll talk about in the subsequent slides. However, there's also two other possible techniques which you can use to exploit these conditions, and which full-size, manned gliders do very, very effectively. And the first one, technique B here, is that you can adjust your airspeed so that you fly at a higher airspeed through air which is going down, which is sinking, and you slow down where the air is rising in the lift, where the thermals are. And even without stopping to circle, this will allow you to get a benefit. But you can also combine it with the circling, the thermaling flight path. You can combine those two techniques to get additional benefit. And this is a feature which is currently under development. The second half of my talk, I'll talk a bit more about the progress towards that. But there's also a third technique, which is kind of on our future roadmap, which is to actually actively navigate the aircraft, so that we're not just flying in a straight line through whatever thermals and sink we encounter, but instead we're picking our way from thermal to thermal and along lines of lift, so that by adjusting our horizontal flight plan, we can fly more through lift and less through sink. So the first existing feature of the code we'll talk a bit about is the variometer feature. And the purpose of the variometer is to try and back out what the air around the glider is doing using the measurements that the autopilot on the glider actually has at its disposal. This can be done by effectively measuring the climb rate of the glider and then adding on various corrections. So there's two principal corrections at present. So the first one is the natural sink rate of the glider in still air, the glide polar. So even if the air is not moving at all, the glider will descend at a rate which is related to the airspeed it's flying at. And that's related through the glide polar. And the second correction is an acceleration correction. And this arises because if you imagine doing a steep pull-up in still air, that would result in a climb rate. However, you'd also be decelerating. So we can add that in as a correction to improve the estimate. And this estimate can be used for various purposes, and there's various filters with different timescales for different types of decision making. So it can be used to decide when to stop and thermal. It can be used for actually adjusting the flight path within that thermal to better harness energy, and then it can be used for decision making as when to give up and leave a thermal. So the glide pool I've already mentioned, which is the sink rate of the glider as a function of its airspeed, even in still air. And in the implementation as present, there's 3 parameters which describe or parameterize this function. The first one is the K parameter, which is proportional to wing loading. And what this does is it doesn't affect the glider ratio, but it moves it to different airspeeds. And this is why full-size gliders have a good glide ratio, but it occurs at very high airspeed because they have a much higher wing loading than our small models do. The second one is the CD0 parameter, which is related to the zero lift drag. And this kind of comes in through the sort of aerodynamic cleanliness of the design. So if you imagine a very sleek and streamlined glider versus a kind of fairly rounded glider with lots of antennas and so on hanging off it, that would be the difference between the value of the CD0 parameter in your glide polar. And the predominant effect of this parameter is to adjust the rate of sink at higher airspeeds. So on the middle graph there, you can see it doesn't make too much difference, the different colored lines at the lower horizontal speeds. But the faster you go, the bigger a difference it makes. And the final parameter is the polar B parameter. And this is really related to the change of drag with lift. And it's mostly related to the aspect ratio of the glider, how skinny the wings are, as well as some other parameters of the design. And what this principally affects is the sink rate at the lower end of the airspeed spectrum. And its effect for our kind of typical range of parameters with model gliders doesn't have as big effect as the other 2 parameters do. So the kind of second component of the existing set of features I want to talk about is the management of the flight mode and the throttle. So currently, thermals can only be detected when the aircraft is gliding because the propulsive effect, the thrust from the motor, would disturb the estimate of what the air around the glider is doing. So the code will automatically suppress the throttle when appropriate to allow that detection to take place. However, there's kind of checks and balances on that. So as the glider descends, if it doesn't then find a thermal, the code will automatically allow the throttle to run again, and it'll climb back to a suitable altitude to start that search again. However, if it does find a thermal along the way, that's specified by the soar v-speed parameter. So if the air is estimated to be rising at a rate which will allow the glider to thermal at a vertical speed of soar v-speed or greater, then the code can automatically trigger into thermal flight mode. And there is an RC switch option to suppress that capability as well if you don't want it to do that. But it can do that automatically and start thermaling. And then it will revert to the previous flight modes under a number of conditions. So if the thermal climb rate drops below that specified value, or if it reaches the maximum specified altitude, it will go back to the flight mode you started in. And the 3 flight modes which are sort of supported as the kind of the baseline flight modes from which to switch are auto flight modes. So you can do a full auto mission, and it will stop and thermal if it finds something along the way. or you can fly more interactively in flyby RB mode or cruise mode. The third component of the existing feature set is the ability, once you have detected a thermal and stopped to circle in it, you can then, the code will adjust how the aircraft flies within that thermal to maximize the climb rate. And thermals, as we kind of saw in the previous videos, they're typically very irregular and turbulent. No two thermals are the same, but they do have some common features. So they will generally have an area of stronger lift within the thermal, typically somewhere in the middle, but there may be multiple areas of stronger lift. And the best strategy to maximize the climb rate of the glider once it's in a thermal is to circle around one of these cores of stronger lift. And in the code, we use a model-based strategy to do this, which requires that we have a model of what this thermal distribution of lift looks like. And we use a fairly common approximation, which is the Gaussian distribution of lift, which you can see here on the right, which has some of the right features. It has an area of stronger lift in the middle, which then has a smooth taper off towards the sides. Now, this is obviously not a physically accurate approximation of what a real thermal is doing, because it doesn't represent any of the turbulence or the non-regularity of real thermals. However, it is close enough to be useful, even though it's definitely not a fully correct model. So what we do with that model is we use the measurements from the variometer to feed into an EKF-like algorithm, which then estimates the 4 parameters of this model to effectively try to figure out where the center of the lift is, how strong it is, and how broad it is. So those are the 4 parameters of this model. And the algorithm is EKF-like because a lot of the complexities of EKF are kind of simplified out this implementation, because we don't model any of the time dynamics of a thermal. So we don't try to update the states over time. We assume that it's fixed, even though in reality it's not. And we deal with any changes over time by just process noise in the estimator. And another major simplifying factor of this implementation is that we only have one measurement. On any time step, we only have a measurement of the local vertical velocity from the variometer. And that again simplifies the maths down quite a bit to keep that implementation quite simple. And it's interesting that even though we only have one measurement at any one time step, because we're taking multiple time steps at different positions, we're able to build up this model of the 4-parameter thermal over time. And as we saw before, the thermals drift with the wind. This is captured via a feed-forward term. So this estimator doesn't have to try to keep up with the wind drift. It already knows that it expects the thermal to drift with the wind. And then the estimated position of the central core of the thermal is then used as the target loiter point using the L1 controller. So this is a kind of result that you get from applying this. This is a plot of a climb in a thermal. And the kind of multicolored trace is the track of the aircraft colored by the vertical air velocity it estimates to be in that position at that particular time. And the blue line in the middle is the estimated location, central location of the thermal that it's trying to track. You can see at the bottom of this, when it first enters, there's quite a lot of variation in that estimate, and then it settles down a little bit as we get quite a constant climb rate in the lower third of the thermal. Then as we get higher, as we saw before, thermals are very irregular, so they change shape over time, and they don't fully obey the drifting of the wind that it expects. So in this example, we start to encounter areas of sink on the kind of the westerly side of the thermal. And at that point, the estimator tries to shift the estimate to better center in the lift and move the aircraft more to the east, to the kind of right rear of this plot. And as I mentioned, there's four parameters, and those are basically the states of this estimator, and they evolve over time, like in this example. Now, recent progress kind of within this set of features. There's been a large number of tweaks driven by the increased level of testing that we've had in action environments. So that's led to a number of improvements to various aspects of how the variometer functions, and also various factors about how the EKF thermal centering operate to make it more robust and avoid some vulnerabilities that were found and improve the performance in a wider range of conditions. And the second broad category is kind of improved ease of use of this feature. So we now have thermal flight mode. Previously, we were doing thermaling in loiter flight mode, in a kind of special case of loiter. And that could be quite confusing for users, but also it limited, it meant that you didn't have loiter available for normal loiter type things. So separating that out gives us better flexibility and makes it a bit clearer to the user what's actually happening when the aircraft changes flight mode. So that kind of separation out has also enabled some other features to be added. So the first one is the separate parameter for the bank angle or the flight path radius to use when thermaling. So again, previously we were using the general loiter radius. And this was not very flexible in that you had to change that parameter if you wanted to do something other than thermaling, you'd have to switch it around. But also it meant that the default values weren't very suitable for thermaling, whereas having a thermaling specific parameter allows us to have a more general default that'll be more suitable for a wider category of users. So flyby-wire and cruise climb capability. So previously, the ability to automatically climb back to altitude and start gliding again to search for thermals again, that was only included in auto mode. It wasn't included in flyby-wire or cruise mode. And what would happen in flyby-wire and cruise mode would be that the aircraft would descend to the minimum altitude, and then it would go into RTL mode, and that wasn't very satisfactory for users, especially people flying long distance with FPV. So having this ability to climb back to altitude and start another thermal search is much better for those users. We now have more RC switch options. So the user, by toggling the switch, can invoke different actions. So if they're already thermaling, it can tell the aircraft to leave the thermal. And we also have a kind of a middle option on the switch. So we have a switch option to completely disable soaring. We have a switch option to enable all the features. Then we have an intermediate position which enables gliding and enables the variometer, but it disables automatically changing flight mode. So the user can still trigger thermal flight mode via their mode switch, but the code won't do it automatically if they don't want it to. We've done a number of documentation improvements to make the setup process easier for users. And we've also developed a glide polar calculation spreadsheet tool to help them estimate these three parameters I mentioned before, based upon the measurements of their glider and the results of glide testing in still air. So that kind of sums up the current state of the code and the recent progress made on those existing features. So that's 20 minutes in. So I'll pause for any questions at this point before we go on to kind of the areas of active development.
So I'm curious, Samuel, about the radius. I mean, you're trying to circle the core of a thermal. Clearly, there's more lift towards the center of the core. So, that would tend to push you towards a narrow radius circle to get more of that lift. But then you'd be at a high bank angle, so that's less efficient flying. Is there a sort of a theoretical way to balance that, to optimize that radius? And is that something that is dependent on the flight conditions?
There is, yeah. So, so you're right. So there's a trade-off there between getting in closer to the core of the thermal in the stronger lift, but turning tighter and having a higher drag effectively and a higher sink rate relative to the air. And for any set of aircraft characteristics and set of thermal characteristics, there is an optimum thermal radius and bank angle that gives you the best climb rate. However, to come up with that optimum, you need to have a good estimate of the distribution of lift within the thermal, and that really comes down to how strong it is and how broad it is. Now, fortunately, in our implementation, we actually estimate both of those parameters using the EKF. So it would be possible to use that information to dynamically update the flight path radius to maximize the climb rate. So that might be a future area of possible improvement. There is one caveat to that, which is kind of subtle, but even though we have these four parameters that characterize the thermal, when we're in a constant steady state turn around the core of the thermal, two of those parameters become confounded and they become difficult to estimate independently. And those two things are the strength and the radius. And you can kind of understand this by thinking about if you're in a very strong thermal, but it's very narrow, versus a weaker thermal, but it's very broad. At some radius, the updraft strength will be the same. And if you're thermaling at that radius, you can't tell whether you're in a strong narrow thermal or a slightly weaker broader thermal. So those two parameters are quite difficult to estimate. And that's why up till now, we haven't tried to use that information to dynamically update the bank angle, because they tend to become slightly confounded.
How much would you need to weave in the circle if you had a sort of a rippled circle, you
Right.
know, like a sewing pattern type circle, you know, would that give you enough observability?
It would, yeah. And the nice thing about the EKF implementation is that it does have a covariance matrix. So even though it can't accurately estimate these two parameters, what it knows that it can't do this from the observability calculations. So it knows that these two parameters are confounded. So the covariance term on those two states becomes very high over time, because it knows it can't independently estimate them. So as soon as you actually go out of a circular flight path, it will very quickly use that high covariance term to update the estimates to make them more accurate. So what we actually need to exploit that is a heuristic that says that every now and again, rather than fly a perfect circle, fly more of an oval to actually get that other information from different radii.
Could you even fly like a bow tie pattern and actually go right through the middle, and that would give you great lift in the middle at the expense of some steeper bank angles? But that would also give you great observability, I would have thought, if you flew a bow tie.
Yeah, absolutely. And there's various kind of ways of handling this in the literature. So various different groups have tried just perturbing the flight path radius a little bit and see if that improves things or makes things worse. I think that there's some issues with that, just because the thermals are naturally very variable. So you don't really know if you know how long do you need to sample over to actually estimate that accurately. Whereas the EKF, you know, because it has a better handling of noise, it kind of has a more natural way of handling that. Possible future
Thanks very much.
enhancement.
So probably enough questions from me. Anyone else?
Yeah, I mean, I should just point out that, you know, that's exactly what we tried to address with our Bomdisaur algorithm at Microsoft. So so it tries to balance that exploration and exploitation, you know, to explore the thermal and learn the parameters of the EKF, and then, you know, once it's got a good lock, it tries to exploit them, and, you know, it's choosing actions optimally. So it's not necessarily just circling. It could be doing something like a bow tie or whatever it decides is the best way to do that exploration and exploitation, you know, in the most optimal manner. So
yeah, it'd be really nice to get some of those features in.
Right. Yeah.
Can I ask how tight you're turning? What sort of bank angles you're using? Like I used to fly thermal soaring, like, you know, full size thermal soaring, and it was actually one of the first things that got me interested in using autopilots. So yeah, so what sort of bank angles are you holding in the turn, and have you sort of are you working on an optimal bank angle versus lift type equation to choose that?
Yeah, great question. So yeah, I've also kind of in the last couple of years got into full size soaring as well. And with full size soaring, they really turn tight, you know, especially in Scotland, I think, because the thermals are quite weak and narrow typically. But 45 degrees is kind of standard for a full size glider. For models, it's kind of an area or UAVs, it's kind of an area for investigation. So I've found that typically in my testing, a little bit wider works better. So maybe 30 degrees of bank or so works quite well. But that's not really based upon any kind of optimality. That's really just based on experience. So right now we leave it up to the user what they choose. But it would be a great feature to have that calculated dynamically.
Yeah, because even I also fly. Well, I haven't for a while, but model like high performance F3B sort of F3F sort of thermal soarers, and, you know, they crank it like, you know, you notice when you can core a thermal well, and you, especially low down, once you get higher up where I assume you guys are working, you know, perhaps the thermals are so large compared to the aircraft, you know, it's you know, the bank angle is much less important than a full-sized aircraft, for example.
Yeah, that's definitely a factor. So yeah, so the kind of scale of the typical lift structures changes based on how high up you are. So yeah, when you're low down, like the F3B guys and so on, they're kind of turning in tiny little bubbles of lift and little eddies. So they really need to turn tight to exploit them, because they are typically down quite low. And as you get higher up, those structures become more large scale. The kind of areas of lift come together to form larger columns, and that's where the full scale gliders fly, is in the kind of upper half of the boundary layer. For that reason, that the thermals are stronger and wider. And that's where, you know, when we're doing commercial operations, that's where we'll typically be operating as well. So the lift structures are wider there, so we can afford to turn a bit looser. But I think that probably doing that dynamically would be a fairly major effort. So right now we kind of leave it up to the user to specify, but fortunately, there's a kind of, by specifying it using a bank angle rather than a turn radius, we kind of we reduce the variability a little bit, because lighter aircraft flying at lower flight speeds will typically want to turn a tighter radius, and parameterizing that as a bank angle, it kind of comes naturally. So while like a full-scale glider would be turning, you know, maybe a 150-meter radius or something, it might do so at the same bank angle that a small model would turn a 10 or 15-meter radius.
The prediction, your Gaussian lift model, that would sort of somewhat, that should be sort of spitting out like an idea of the radius of the lift, and from that an indication of what some idea of what at least a suboptimal radius would be.
That's right.
So there like a very least a sort of a maximum radius that you should be turning. So there might be an opportunity at least there to sort of say, look, you should be, we perhaps should be increasing our bank angle here, or something like that.
That's right. Yeah. So yeah, I think we'd probably, to do something like that, we need what Tridge mentioned and what Ian did previously, which is to perturb the flight path to gather that additional information to improve the confidence in that estimate. That would definitely be a nice thing to have in the feature set.
No, awesome, love it.
Hi, Sam.
Hi.
So you mentioned that you're suppressing throttle specifically to be able to detect the thermals. What would you need in addition to be able to remove that constraint? Would you need to make any additional measurements so that we might be able to use motor gliders to push through regions of like high sync as well?
Yep. So next slide, please. So right. So this is an area for kind of active development. So shall I continue with this, or are there any other kind of burning questions before I continue on? Okay. So yeah. So right now, to sum up, we only detect thermals when there is propulsion suppressed, because we don't have an adequate correction for what effects the propulsion introduces. And this actually can cause a problem in some conditions. So if we have a situation where we want to use soaring, we want to use thermaling, but the conditions aren't quite strong enough to remain airborne purely using thermaling, we end up in this kind of gliding descent, and then followed by a climb, and then a gliding descent. So we end up with this kind of saw-toothed climb-glide sequence. And this can be a bit of a problem. So for kind of a few different types of vehicles. So if your vehicle has quite a low climb rate relative to its descent rate, this can mean that you actually spend a substantial proportion of the time climbing back up before you start another glide. And there's a good chance that you'll be climbing straight through the thermal that you'd like to be harnessing, so you miss it. And then secondly, for vehicles which have very highly optimized propulsion systems, so the Crescent Down Aerospace K1000 is definitely in this category. We spend a long time designing propellers and optimizing propulsion systems to get a very low cruising power. So the efficiency is optimized at one cruising condition, which is a steady state, constant altitude condition. And the kind of climb glide cycle is overall less efficient. This actually shows up in some of the data from our 12-hour flight, which you can see here. So there's a couple of features to point out in this. So what we have is a few different kind of phases within this flight. So we have the takeoff phase right at the start, followed by a steady state cruising phase for the first sort of 4 hours, really. And then after the first roughly 4 hours, we start to see thermal activity. And we want to start utilizing that using Soaring. However, the thermal activity isn't quite strong enough, as I mentioned, to have a sustaining flight all the time, with those times where we're descending and hitting the minimum altitude and motoring back up. And due to the reduced efficiency of the propulsion system when climbing, this actually results in an increase in the average power for those time periods. So even though we're spending some of the time thermaling, the reduction in propulsive efficiency is still overcoming that, and our average power consumption is higher in those points. So that happens at the start of the day, or kind of when the thermals are just beginning, and it happens at one point in the middle of the day when the thermals just happen to die off over our area. Then it happens again towards the end of the day when the thermals start to taper off. And all three of those occurrences are accompanied by an increase in the average power consumption. The yellow is the solar generation for this vehicle, so not relevant to this discussion. So that's a problem. So we'd really like to get the efficiency back to, or the average power consumption back to no greater than the average. It should really be better than average. If we're doing some thermaling, it shouldn't be higher than average. And also for aircraft flying missions which have restricted altitude profiles, reducing this climb glide cycle makes it easier to interface with ATC and to remain within your altitude permits. So to kind of reiterate exactly what's happening there, so this is a kind of a simulated example of that same mission profile. So takeoff, long period of cruise, constant power, and then period of this sawtooth pattern, which has a higher average power due to the greater power during climb, and then periods of thermaling interspersed with periods of higher power due to climb glide. Now, what we'd really like to do is to get to something like this, where we cruise in steady state, and then we have Soaring enabled, but even if there's no thermals, we want to have the power no higher than the cruising power. And then we want to be able to thermal and not use any propulsive power. And if the thermals die off, we want to go back to a cruising power, but no more than that. And then at the end of the day, we want to go straight back to cruising power and not have any higher power areas. So to do that, we want to detect the thermals from the steady state cruise condition. And this requires us to add on a correction to the variometer estimate. So we had this same equation before, apart from now we've got this propulsive term. And actually we have already all the information that we need to add this on. So the text already knows from its parameters how much specific power it's putting into the propulsive system by looking at the maximum climb rate, the maximum throttle, and the trim values. So we can actually already use this to correct the estimate, and this then allows us to be able to detect thermals straight from the cruise condition, which it kind of has pros and cons. So right now it's implemented as if for testing, it's not yet PR'd as a kind of separate Soaring mode. If you set Soaring enable to 2 rather than 1, you get this behavior. So the pros are that you reduce the user intervention. So for these very long missions, obviously this isn't relevant to most users, but if you're doing very long missions, you don't have to make a decision about when to enable Soaring. You can actually have it enabled all the time because there's no trade-off with this increased power consumption. You improve the efficiency while you're waiting for thermals to fill in. You're able to detect more of the thermals because you're not spending some time climbing through them. You don't have this, makes it easier to interface with ATC due to the reduced altitude variation. And it's less intrusive to your kind of general mission profile. If you're trying to fly a payload and you don't want to be doing this climb glide, then that's better as well. And it's also potentially more applicable to kind of general usage of aircraft. If people are flying, if people are out for a kind of FPV joyride, they don't necessarily want to have this kind of fairly intrusive climb glide cycle that comes about through soaring. Maybe they just want to cruise at a constant altitude, but they want to be able to opportunistically take advantages of thermals if they happen to run into one. So there are a couple of cons, however. So there's once this is enabled, the accuracy of the text parameters then feeds into the ability and the accuracy of thermal detections. So if you're flying in extremely marginal conditions where you really want to tell the difference between a thermal which just allows you to climb at your specified rate and one which doesn't quite, then errors in these parameters will reduce that accuracy. However, it doesn't affect the accuracy of actually centering a thermal, because once we start thermaling, the throttle is then suppressed again, so the accuracy estimate goes back to whatever it was, so that error will be removed. And that those kind of parameter settings just introduce a little bit more scope for user error. But overall, for people who are flying vehicles which are well set up, I think the pros vastly outweigh the cons. So any questions on that aspect before I go on to the kind of next feature under development? 40 minutes in now to the talk. Okay. So the next kind of aspect under development is what I mentioned previously with regards to the kind of second technique, technique B, which you can use to exploit the lifting thermals. And this can be used with the circling flight path or as a second separate method. But essentially, what this relies on is changing the airspeed dynamically to maximize the performance of the aircraft given what the air around it is doing. So whenever we're gliding from a given altitude, what we really want to do is we want to maximize how far we glide, because that will give us the two things. It will give us the widest area possible for detecting thermals. So the further we glide, the more chances that we actually intersect a thermal and start to exploit it. But secondly, we also probably want to make some kind of progress towards whatever objective we have in our mission. Now, if the air is still, when we have the best glide speed for the aircraft, and that is essentially the airspeed which gives you this furthest distance. And this plot shows the glide polar of the aircraft. So it's the vertical speed of the aircraft as a function of its horizontal speed. And this way of drawing it is a kind of graphical method of estimating the best speed to fly at to get the furthest distance. And what you essentially do is you draw a line from the origin of the plot, which just intersects tangent to the glide polar. And in this case, that occurs at effectively the minimum airspeed of 16 meters per second. So 16 meters per second is the airspeed you should fly at to maximize your glide ratio, the distance you can travel for a given height. However, usually in between thermals, we don't have still air. Usually we have some sink, which is balancing out the lifting air in the thermals. And usually we have headwinds or tailwinds, which affect this calculation. So this plot is the same as before, apart from it shows what is the effect of having an additional vertical speed component due to air movement, WZ, and an additional horizontal air movement, WX, due to wind, headwind. And you can see that if we draw the same diagram, we now have a much shorter distance that we can travel due to the effect of these adverse wind conditions. And that then means that the optimum airspeed to fly at is now different. And there's a theory which tells us what's the new optimal speed. And we can again use the same graphical construction technique where we, for this example of 1 meters per second of sink, we move the glide polar down to add that 1 meter per second onto the original vertical speed. And then we repeat that tangent process and we come up with a new airspeed, which as we expect is higher. So if we're flying in sync, we expect to want to fly faster to get through it. And the new airspeed. It's now gone from 16 meters per second all the way up to 21 meters per second, just with 1 meter per second of sync, which isn't actually a huge amount. So it's quite a big change. But usually, to kind of simplify the diagrams, rather than redraw the drag polar, the glide polar, usually we just draw this intercept to a different point on the graph. So rather than drawing the intercept line through the 0, 0 point, we draw it through the vertical point corresponding to the level of sync. We get the same result, that 21 meters per second is the best speed to fly at. And this also works for headwinds as well. So in that case, we offset the starting point of the tangent by the sync speed and the headwind speed. And this example shows that if we're flying in 1 meter per second of sync and 5 meters per second of headwind, now we need to fly at 23 meters per second to maximize our distance traveled. So we're already, we're creeping up and up as we add more and more effects. What if we know, however, that we actually are expecting to find a thermal up ahead of us that will give us a certain climb rate that we expect? Well, fortunately, this theory, amazingly, also works for this situation. And what we do is we add that effect, forgetting about headwind for now, we add the expected climb rate on as an additional vertical offset to the starting point of the tangent. And what this tells us is that if we're expecting to find lift ahead, that means we should fly faster. And what this is now solving for is, rather than the distance that you can travel for a given height, it's actually optimizing now the average speed cross-country from thermal to thermal, which is quite amazing that the same technique works for both scenarios. And it's quite nice that to combine the effects of sync and an expected thermal, you just add those two numbers together as the vertical offset. And this also works fine for headwinds as well. You just add that offset to the graph as well and draw a new intercept. And in this example, we've got the three sort of combined effects, which, if we're flying at 1 meter per second of sync, we've got a 5 meter per second headwind, and we're expecting a 2 meter per second thermal climb at some point in the future. This is now telling us that rather than fly at our 16 meter per second still air best glide speed, we should now fly up at nearly 31 meters per second. So a massive change of optimum airspeed in a fairly realistic set of conditions. Now, typically full-size manned gliders, because they fly at a higher airspeed, so they're typically flying somewhere between maybe 60 and 90 knots for a cross-country flight. The effect of a 10 to 20 knot headwind is actually significant, but it doesn't change this too much, and they can afford to add that on later as a kind of correction. So what they typically do is, because lift and sync, lift or sync in the current between the thermals has the same effect as the expected climb rate in the next thermal, they take those two parameters, lump them together, and they do effectively a 1D lookup for what the best speed to fly is. And they very cleverly do this by adding an additional ring to their variometer, which allows them to adjust their expected climb rate and read off what the best speed to fly is. However, for us flying models or UAVs, typically at a lower flight speed, so it might be as low as 20 knots for a foamy, so that the effect of a 10 to 20 knot headwind is going to be catastrophic. We really want to capture this this effect of wind in our calculation. So we need to retain the more complex relationship. And the kind of graphical solution that I presented before, that can also be written out as an optimization problem. And this is what we have implemented, and this is what is currently being tested to maximize to get the best speed to fly. So there's this rather imposing looking equation, but don't worry, I've solved it for you. And this has really got a few inputs. So it's got V thermal, which is the expected climb rate in the next thermal, and that comes straight from the soar V speed parameter. We've got the wind component along your course over ground, which comes from the AHRS. And then we've got the local wind between the thermals, the vertical wind component, lift or sink, which comes from the variometer estimate. And I said I solved it, but actually there is no solution to this, so it has to be solved numerically. And this is done with a Newton method solver. And what we do here is we just run. So this is the shape of the solution, I should say. So for any So this is the shape of what the solution looks like. So it's a fairly well-behaved solution, which is why Newton method works quite well. And typically Newton method will converge in 3 or 4 iterations, will get you very close to the final answer. However, we'd rather not do, a kind of multiple iterations per loop inside the Soaring controller. So rather than do that, we actually just generate a new solution on every call through the Soaring controller. It just does 1 iteration of Newton, and it starts from the previous estimate from the previous loop using the new inputs. So the inputs change, but they actually change not too quickly compared to the loop rate because these are all filtered estimates. And that means that the previous solution is actually a fairly good approximation to the solution to the current set of inputs. And we just do 1 single updated iteration, and then we use that as the speed to fly. Now, although this method never actually converges because the inputs are also changing on every time step, it actually gives better accuracy than if we were to freeze the inputs and do multiple loops over multiple iterations over multiple loops, because we allow the inputs to change continuously. So it never converges, but it gives good accuracy. And the initial flight data from this implementation has been fairly promising. So in the final implementation, there'll be more smoothing associated with this, but you can already see that there's a correlation between the red in the top plot, which is the local sync rate, and the calculated speed to fly in the bottom plot. Plotting it out like this makes it a bit easier to see. So for any measured local sync rate on the x-axis, we're coming up with a best speed to fly on the y-axis. And this has been binned according to what the horizontal wind speed is. So you can also see that for any given sync rate, a greater wind component, a greater headwind component, which is more negative, results in a higher airspeed as expected. Now there are a few oddities to this plot. So there's a bit of a gap here in that no measured sync rate will result in an airspeed which is between 10 and 11 meters per second. And this turns out to be due to a missing term in one of the special cases we need to implement for when to fly at the minimum airspeed. So that gap will be fixed. And this appears to have resulted in some spurious solutions, which is probably due to this discontinuity and the Newton method not quite converging or not converging adequately on a single iteration. So I expect in future flight testing, once this missing term is input, those spurious solutions should go away. If not, we'll deal with them some other way. In terms of how this is going to be set up, so there's going to be a new parameter, soar cruise airspeed, and for that one, 0 will be the kind of default, which will be disabled, which will mean it uses the trim airspeed in between thermals. Greater than 1 will mean that you just fly a fixed specified airspeed, so it won't do this calculation, but it'll give you the ability to just say, I want you to fly at 15 meters per second as a separate setting from trim airspeed. And then finally, -1 will be automatic, meaning do this calculation and work out what you think is the optimum speed to fly at. So some kind of big pros from this will be improved performance. So I really expect that this will improve a lot the kind of average sync rate in between thermals and allow us to really maximize how far we can travel and generally improve the performance of the aircraft when soaring a lot. Secondly, there's going to be less user intervention. So right now, when running these long missions on the K1000, but also more generally, the user, if they're flying through a large area of sync, they might interactively set up a higher airspeed to get through that. And this will now automatically be taken care of. Potential cons, so because this relies on a number of different estimates, for example, the polar parameters feed into it and various other things, there's a little bit of additional scope for user error in setting those up. This will be more of an advanced feature to enable once the aircraft is flying correctly in other ways with soaring. And then secondly, there are some potential new couplings between errors in the glide polar and how the speed to fly theory operates. So that's still to be worked out whether there is any instability there, and if so, how we'll deal with it. But I don't expect it to be a big problem. So to wrap up, I think it's a really big potential benefit from this method. It does need a bit more refinement. You can see here one plot from a flight of the K1000, where this is quite nice because it shows the amount of lift and sink we're measuring as we fly between thermals. And here you can definitely see that there's areas where we're flying through neutral air or slightly rising air, and then areas where we're flying through big sink. So this adaptive airspeed will really help out with that. So that's kind of the speed to fly. So to wrap up, so there's only 5 minutes left, so I'll wrap up fairly quickly. So with soaring in general, as we've already discussed with some other possible improvements, there's massive potential for future optimizations and future features to improve the performance of this kind of aircraft. But also, I think that the current features would really benefit from a wider community of users and testing. And towards that, there's a few things I've been looking at. So improved documentation I've already mentioned, and I'll continue to work on that to make it easier for people to get into it. But also there's the potential for maybe opening up to operation of aircraft which don't have an airspeed sensor, which is a current stipulation is that the aircraft must have an airspeed sensor. It may be possible to relax that, obviously with some performance decrement, but it might still be useful to get those users enabled. So more challenging simulated test cases would be nice. We have a fairly simplistic test case in the SITL simulator, which is run as part of the auto test suite. And then we have some more complex interactive simulators. However, having some more realistic automated test cases would be really great to validate some of this more advanced capability. And the last one I have here is a lot of these features are quite difficult to reliably benchmark outside of simulation. And that's because the conditions we're trying to exploit are fundamentally stochastic and non-repeatable. So if you're trying to fly the same aircraft twice with different versions of the code or different features enabled, you can't expect to get a reliable idea, except in a very kind of probabilistic sense, about whether the change made an improvement. One way of getting around that is to have multiple aircraft flying in the same weather conditions. And this is something that I think is going to be very big this year. So I've actually got set up with multiple almost identical aircraft, which I'm going to use to do back-to-back testing of different variations. And then finally, to kind of leave you with this very quickly. So this is the kind of future potential for the third technique I mentioned, which is doing more intelligent route planning across between different thermals. And this, is really a kind of future effort, and it may be something which has to run on a companion computer or a more complex system. But the idea with this is that we have a bunch of information already about where we might expect to find better lift conditions. And that can come from knowledge of the terrain, so different terrain features are more likely to generate lift and thermals, as well as different weather conditions, for example, the wind direction and the sun angle. So we might use that to work out a kind of a priori map of where we expect to find thermals. However, even better might be if we do have multiple aircraft for certain missions. This is more probably for the commercial, the industrial application. But if there are multiple aircraft flying in a swarm, then they can start to share information. So if one of them happens to encounter a thermal, it can then communicate that to the other aircraft. They can use that within their route planning to do a better job of preferentially flying through better conditions. So that's the end of my talk. So so we're quite close to the top of the hour. So if there's any questions, let's have them quickly.
Well, we don't need to rush it. We can go a few minutes over if we need to. It's a fascinating talk. I really, really appreciate it, Samuel. I'm very interested in the non-airspeed operation. And one thing that might be worth looking at is we could use the replay facility in the EKF to allow us to rerun flight logs without the airspeed sensor and look at the estimated airspeed and estimated wind so that means any of your flights you do with an airspeed sensor, you could then run a script over it to see how well it would have done, at least on the airspeed and the wind estimate, which is the key thing, I guess, if you hadn't had an airspeed sensor. That might allow you to start providing some advice on how well it might perform and make that decision as to whether it's recommended. That should be, we'd need a small tweak to replay to allow us to disable the airspeed input, but that should be quite easy.
Yeah, that'd be really interesting. And maybe as a kind of extension to that, we could also bring in some of the soaring features into the replay. So the soaring estimator, I have a kind of a local replay capability using my MATLAB tools. But if we could do that same technique and assess how much impact there would be on those bits of code, that would also be be quite useful in making that decision.
Yeah, yeah, definitely worth looking at. So questions from others?
Yeah, really great talk. Thanks, Sam. What simulators have you integrated now with this?
Yeah, so I think back when FrigateBird was running, you guys did a lot of work with Silent Wings, if I remember. So there's that one which hasn't really received as much use as it should. But the one which I'm working more with now is called Condor 2.
Right.
And that one's quite interesting because I think it's a bit more actively developed than Silent Wings is. But also it's got a really great community around it. So at my kind of local full-size soaring club, they do weekly sessions where they will go and fly in Condor. And even amongst those very experienced soaring pilots, it's got a great reputation for the accuracy of the weather conditions. I think they described it as frighteningly accurate, frighteningly realistic. Yeah. So that's a really great kind of recommendation from that community about how useful that might be for actually tuning up some of these features.
But you haven't got that working with Settle yet. That's future work.
So it is working. So it does need a bit more work. But yeah, that for future, I think that's going to be quite important.
Yeah, great. Is there any plans to maybe do some parameter learning as well? Like the glide. I think the glide polar. Maybe for some users that's something they're just not really going to bother with, or maybe they change the weight of they put some ballast on and forget to change it or something like that. Like maybe being able to learn that glide polar would be quite a useful addition, perhaps. Is that something?
Yeah, that's right. So yeah, so that's actually implemented, and it's had some testing already. I haven't included it in the talk just due to time, but that is implemented, and it does work actually. I've used that on my gliders. However, that again does need a bit more testing, and it doesn't completely remove the possibility of error. So, but to accurately estimate the glide polar, you need to be flying in still air conditions. That's one thing, and you also need to be able to hold airspeed fairly accurately as well. So it's kind of an open question whether it's better just to estimate from glide testing or whether to use this online learning. But it does exist, so I'll point you at it for your testing as well.
Right. Mm-hmm. Thank you.
All right. So if that's the end of the questions, then thank you very much to Samuel for a fantastic talk, really enjoyable. And I greatly appreciate the detail in the slides, and looking forward to seeing some flying in our local flying field with Ian. So up next, I'll just switch over the recording, ready for starting recording the next talk. And up next we have Rishabh. And so Rishabh, are you ready with your talk?
I am. Am I audible?
You are audible. Yes, that's looking good.
I am very much ready.
Okay, you ready? All right, so I'll start recording for the next session. And so welcome to Rishabh. So Rishabh's going to be talking about the object avoidance changes in ArduPilot. There's been a lot of work in object avoidance over the last year. And so Rishabh has been leading the charge on that. And over to you, Rishabh.
Just a second, let me just share my screen.
Sure.
Right. Am I visible?
Yeah, looking good.
Right. Okay. So thank you so much, Andrew, for the introduction, and congratulations to the last speaker. That was an amazing, really interesting talk. So moving on with obstacle avoidance. Right. So not a lot of you actually know about me. I'm a fairly recent addition to ArduPilot. So just a little introduction about me. I'm an undergrad student, fairly young, 22 years old and I study at BITS Pilani, India. It's a famous university here in India. And the first PR I made was a little, almost 1.5 years back in June 2019. And actually the very first experience I had with ArduPilot was back in my first year in college, when I saw a couple of seniors who were flying with those APM 2.6 boards, and it was just amazing to see how well those even those old copters flew. So I decided, let's just gather a team of people and make ArduPilot supported copters just for fun. So we got around, we have a bunch of really enthusiastic people, and we got about 100 people to sign up, and all of us actually made more than 100 quadcopters and flew it, and none of us actually knew how to fly them. So it was all a huge scramble with all of us flying in stabilized mode and none of us actually knowing what to do. And we broke about 50 propellers that day. So that was my introduction with flying. And of course, the first PR came a few years later. And subsequently, I started preparing for Google Summer of Code. For those of you who don't know what Google Summer of Code is a 3-month program. Now it has been shrunk to about half, but it's a 3-month program that Google sponsors for students like myself to interact with open source organizations and work with them, work with the industry leaders in, but only in open source organizations, much like ArduPilot. And I was subsequently selected as a Google Summer of Code student at ArduPilot, and was tasked with improving the obstacle avoidance features that we support. So obstacle avoidance was a recent addition. It's not as old as most features in ArduPilot is. It's something that is quite recent. So my task was to figure out. Actually, Randy did most of the work of figuring out what was there to be improved and what were the bugs. But my job was to fix them. Ever since then, I have been an active tester, an active developer, and most recently, this just March ending, I was also selected to be part of the dev team, one of the newest members of the ArduPilot dev team. So thanks for that. Just an outline of what can you expect from this talk today. So today I am just going to give you an overview of the entire setup of how we gather data from the sensors, and how do we process it, how do we store it on board, and then how do these algorithms actually use these data. And so about half the presentation is actually just videos. It's like a movie. The first half might be a bit boring about gathering the data, but the rest of the half is just purely videos, and should be fun. So obstacle avoidance is of majorly two types in ArduPilot, and that's because we have the autonomous flying modes, and we have the semi-autonomous flying modes, or the manual flying modes, where the user is taking control themselves. So for the autonomous modes like the auto or guided mode, we already know where the flight is heading to, right? We already know the general direction where the vehicle wants to go to. So we can plan a path, we can avoid obstacles, we can plan around the obstacles, we can do all that kind of stuff. But with manual modes, we really don't know where the user wants the vehicle to go. You're going straight 1 minute, and the next second you turn right, and you can do whatever you want. So there's no just to mention that there is no way you can plan ahead. So there are two different algorithms that we use to deal with this. So the first part of the presentation is going to be explaining you what simple avoidance is, which is basically done in manual modes. And the next part would be on bendy ruler and Dijkstra, which is done in autonomous modes, which are basically part of a path planning suite. If you see under the manual mode section, just a second. Yeah, if you see under the manual mode section, I have two different algorithms, which is one is simple avoidance and one is ping pong method. I don't think it's named ping pong method, but that's just how we refer to it. I think Randy named it named it this. And so simple avoidance basically works by reducing velocity in the direction of an obstacle. So if the if the vehicle is approaching an obstacle, and we have calculated that it's definitely going to break the margin around an obstacle that the user has set, then it just reduces the velocity. Whereas the ping pong method, or which does not really require GPS, it's done mostly in altitude hold modes. That one actually works on angles. So if we are pitched 15 degrees forward and we are approaching an obstacle, it reduces that pitch to say 10 degrees or -5, -10 degrees, so that we go away from it. So the proximity library, right? So many people actually, especially in the discussion forums and while talking about avoidance with me, they kind of confuse it with the rangefinder library. The rangefinder library is not the same as the proximity library. The rangefinder library is used by plane, it is used by copter, it is used by rover, but the proximity library is only used by copter and rover. The rangefinder library basically takes care of those 1D lidars that only provide point distances to just one orientation. Whereas proximity library actually handles lidars like you see on the bottom right corner, the rotating RP lidar, where you have 2D data that is being fed directly into ArduPilot, and these data can be 10-20,000 separate data points a minute, and the proximity library actually does all this calculation to help us store that data. Right. So the 10,000, 20,000 different points that are possibly entering into ArduPilot, we can't store. I mean, we'd love to store all those points, but it's not physically possible, right? For us to store that and for us to process it. So what the proximity library does is it makes a boundary, it makes a filter, or you can call it a filter, that reduces those points so that we have an easier time in storing and processing it. So this is what the proximity library does. You can imagine, imagine yourself to be the quadcopter right here, and imagine yourself in a flexible hula hoop, holding a flexible hula hoop. So this is what we call the mini fence, and this mini fence is 8-sided. So we could have 100 different obstacles approaching. So each face, each of the side is called a sector. So we could have 100 different obstacles on each sector. So 100 obstacles here, 100 obstacles here, 1,000 obstacles everywhere, all along these faces. But we only pick out the whatever is at the least distance. So whichever is the closest in this region. So maybe we have obstacle here which is 5 meters away, an obstacle here which is 10 meters away. But we only pick out the 5-meter one because it is at the closest in this sector. So basically the 10-20 20,000 different points that I was talking about earlier, they are reduced to 8 points around the vehicle. And so when there are no obstacles available, if the copter is just flying happily and there's nothing in its path, this is how the fence looks. It is at its default state. But as soon as say there's an obstacle that approaches from G side, what we do is we bend that hula hoop or bend that fence, and we make it like this. So you see the obstacle, you see what the situation is, but what the vehicle sees is this right here, and this is what the simple avoidance acts towards. So so if you were the vehicle in the middle, you're going to look back and see, okay, everything's fine at B, C, and D. But if you look forward, you see, oh no, G is approaching too fast. We must do something about it. So this is how it was done in 2020. Right. So as is visible, this is very much a 2D algorithm, right? So for example, I told you we have a object here at 5 meters, we have an obstacle here at 10 meters. But what happens if obstacle is approaching from the top or the bottom? If it's approaching at 10 degrees pitch, how do you handle that? What if there are 3 obstacles, each at different pitches but at the same sector? What happens then? So this was not really a problem until very, very recent times, because most of the sensors, like the RP LiDAR that we use, they only gave us 2D data, right? They didn't really we didn't really have the access of 3D points. So why bother with all that excess code and the code that is never going to be used? But now in 2021, we have these fantastic new cameras and the fantastic sensors that have the ability to give us 3D data. So, just to speak a little bit about stereo depth cameras, this is a D4 Intel RealSense D455 right here on the right, and these incredible devices, they are cheap. They are, I mean, relatively cheap. They are small, lightweight, and they have the power to give immense amount of data in one go. So I'll show you, the sort of data that this thing gives. And just to give you a little idea of how these sensors work, because we have been working quite some time on them. So it very much works like a human eyes. So this is like your left eye, and this is like your right eye. The very oversimplified way of working is that the left eye and the right eye, both of them see the same point, but of course they're slightly shifted, right? So if you close your left eye, or if you close your right eye, the vision is going to be slightly shifted. So it uses this baseline, this distance between these two sensors, and it uses that shift in the image to calculate the depth of the obstacle. It's a very oversimplified explanation, but we can have a chat after the conference if more people are interested in knowing how these sensors work. Apart from that, we also have an incredible RGB camera in the center. So what we can do is that you can run all those ML AI algorithms that classify obstacles, and then you can figure out in camera coordinates, you can figure out u comma v, which is what are the coordinates of, say, a human or a toddler walking across, and then you can figure out what the XYZ, the actual physical coordinates of that body frame coordinate of that obstacle is. So that's why these cameras are fantastic, and these are being these are being made better every day. So up until last year, we only had the D435i, which was the best camera that Intel RealSense had, and those gave us 10-meter range. But now we have the D455, which gives us 20 meters range easily. So these are being developed every day, and it's just exciting to see where these are heading. So back when I got these cameras, I did not, have any source on, how good these cameras are or how do they work. So I created this YouTube video, which has actually become quite famous online now, because a lot of people are, seeing how the camera functions, and what is the comparison between the D435 and the D455. This is what you get from the cameras. On the bottom, you see there's the RGB normal camera, like a FPV view. And on the top, we have the depth visualization. So the way this visualization works, this is an incredible amount of data, right? So the way this visualization works is that, the areas in red, they are the closest to the camera, whereas the areas in blue, they are the most further away. So you see those trees in the background that you can see in the RGB camera, they are visible with the blue background, and the ground, which is very, very close by, that is in red. And what I've done is that I've divided this entire view into a 3x3 cross section. And I have printed down, the minimum, what is the minimum distance of what I can find in this grid. So for example, land is 1.65 meters away, whereas those trees in the background are 15 meters away, as can be seen on the top. So the rest of the videos, they're going to have similar representation, and now what these values, the red values are, and what this grid is. So yeah. Just a static test of how well these cameras function. And, this is connected to my laptop. So we're getting about 30-40 frames a second. It goes as high as 60 or 75, depending on, what API you use. If you use C++, it's much faster. If you use the Python API, it's much slower. But the point being that it's just incredible about how much data that we are able to gather from these sensors. Right. So this brings us to the question, now, as you saw, this hula hoop kind of thing that we do, this mini fence thing that we did in 2020, this is no longer sufficient, right? We need something that if a user tells you, there's an obstacle at 2 meters up, 3 meters to the right, and 5 meters away, you need a way to process that data. And it was not possible up until now. So the recent work that me and Peter Barker and Randy all together have done is that we have converted this mini fence to a spherish shape like this. So if you can recall, I told you that if we have like 5 obstacles, one is here, the other one is a little further away. We pick out the closest distance. The same idea has been extended to 3D. So so this is one, we call this faces. So before we used to call it sector because it was like a 2D kind of thing, but now we call it a face because it's more 3D. So this face right here. So we could have 100 distances along this face, and we'll just pick out whichever is the closest distance in each face. So we have 5 layers of these faces, from top to bottom. So there's one in the middle, there's one in the bottom, there's one between middle and bottom. So there are 5 different faces that we have. So before we only had the ability to store 8 obstacles at the end of the day, but now that has been transformed into 40 obstacles, which is all around the vehicle, right? It is 3D. And just to give you a visualization of how this works. So this is a tiny tool that I have built to, not a lot of people understand the visualization of these mini fences that we make. And this is a tool that is still sitting in a local branch, and I intend to push it up to master so that other people can also test it. I have not really found a good way to do it yet, because this was a really hacky way that I figured out. So on the left screen, you'll see the normal Citadel view. And the green fence is actually an obstacle. It is treated as a proximity obstacle. So this is at the default state, right? There's no obstacle detected, and this is how the fence is. But you realize as soon as I give the command of go forward, I push the sticks forward on loiter, you'll see that the fence starts coming in together. And that is basically how, so before, in 2020, we only had this middle sector, this middle layer right here, the middle one. But now we have these 5 fantastic layers that helps us, get 3D. And, they're going in together. And that's because at this stage, you'll see the vehicle is actually quite near to the obstacle. And so this is the view that the humans see, right? This map right here. But this is what the vehicle sees. This is what the proximity libraries see. This is what the avoidance libraries see. And if I was to rotate, since this is body frame, if I was to rotate this, rotate the vehicle, the points switch, like the different points come together, but the circles themselves don't rotate, because this is very much body frame. This is not earth frame. And if I was to bring back the vehicle to its original position, then you'd see that the fence points again. This is again what the avoidance libraries is seen, and this is happening. This visualization is happening in ArduPilot. I mean, the graph is being built in a Python script outside, but all of this is being built inside the proximity library. So this is the most significant change that we have brought about in 2021 in the proximity libraries. And this has been merged to master, and I'm really excited for Copter 4.1, Rover 4.1 release that are going to be able to use this. Apart from that, there is now a filter on each of the face. So what happens was, so we had a bunch of users complaining, for example, SF40C, 95% of the times the data was fine. But what happened was that there was this one awful second where the distance would jump from 10 meters to like 0.5 meters. And that's a nightmare for avoidance, right? Because if it's seeing an obstacle at 10 meters and all of a sudden the sensor reports obstacle at 0.5 meters, it's going to react to it, right? And we had no filters available. So what I did was I added a low pass filter, which adds a basic degree of smoothness as well to the data. And the cutoff filter to that, the cutoff frequency to that filter is very much customizable by a user settable parameter. So I'm also, I'm hoping that any noise that people were attaching, random rangefinders from different companies and seeing their raw noisy data. And this is just a good way of making sure that connect whatever sensor you have to ArduPilot, but we've got the noise covered. You don't need to worry about the copter going crazy mid flight, just because a sunlight came for a split second inside the sensor's view. And another sort of nightmare that we face with avoidance is ground detection. So copter doesn't know where, if the ground is an obstacle, or if it's just ground and you need to ignore it. There is no way of knowing. And so what happens is that when you're taking off, it sees the ground below. The lidar, they see the ground below or the grass as obstacle, and it immediately reacts to it. Which is scary because you're so low that any reaction could lead to a crash. So we have implemented this very elementary ground detection inside Proximity Library, which uses the downward facing rangefinder, and it tries to filter out any the 3D point that is on the ground. So for example, the downward facing rangefinder is reporting 2 meters altitude, and we feed in an obstacle which is also 2 meters below. So we immediately know, this is a point that we need to filter out. This is the ground, just ignore it. And this again is we can disable it if we want to. Users are not forced to use this, but if you're someone who is having troubles with ground, make sure that you try this new feature in Copter 4.1. It is of course not a feature in Rover because it doesn't make sense there. Right. So what's missing? We've done a lot of work in the proximity drivers, like a lot of it, but there's still some stuff missing. So the first one being that we've not really received a lot of support queries on, but I'm sure someday they'll come when avoidance is a little bit more being used. So we only support one type of proximity sensor at a time. So you can't connect, say, two Lightware SF 40Cs or 45Bs, or you can use 8 rangefinders, but that's a different thing. You can connect 8 rangefinders at the same time, and proximity libraries will, they will support that. But as far as proximity drivers, proximity sensors go, you can only use those 8 rangefinders. Then you can't connect a SF40C with it. So that's one limitation of the proximity libraries. Now, the other thing is that the rangefinders, if you go see the rangefinder orientation parameters, it is defined to, it is limited to 8 orientations, yaw 45, yaw 90, yaw 180. It is only limited to those orientations, and as well as, upward and downward facing rangefinders. But now, since we have a 3D boundary, like what I showed you just a minute back, we can actually extend the rangefinder orientations to be much more. And I don't think this is a big deal. I most likely already have a basic working PR, but with a little bit more testing, I'm sure that we can get this done. Apart from that, we don't really have good settle testing abilities with proximity library. So this, for example, I was forced to make this visualization, but it took quite some time to make this visualization actually. So it'd be great. And settle being 2D in itself, it's kind of tough to have 3D testing abilities purely settle wise. And how do we get around this, and how do we use other 3D simulators? That is towards the end of the talk. Yeah, so better settle testing abilities obviously is, and autotest is something that is missing. And another problem is this boundary is not closed. So this boundary right here, this boundary that you see, it has 5 layers, but it does not have a pitch 90 and a pitch minus 90 layer. So it is very much open from the top and bottom. So if right now, if you were to try to feed obstacle that is pointing upwards, it is going to put it on this layer, the topmost layer. It is not going to have this. It's not going to have a point directly upwards, which is also something that I have been intending to work on, but haven't found the time yet. So any questions regarding proximity library? All right. So moving on to simple avoidance. Right. So the proximity library is like a stepping stone for simple avoidance, right? And simple avoidance is the type of avoidance that we use in manually controlled flight mode like loiter. So not a lot of people know how, a lot of people have used simple avoidance, but not a lot of people know how simple avoidance works. So we have two modes inside simple avoidance. One is the slide mode, and one is the brake mode. The brake mode basically just stops in front of the vehicle, which is not really that complicated. But sorry, it just stops in front of the obstacle, which is not that complicated. But the slide mode, what it tries to do is it tries to slide around an obstacle. And the way that it works is quite simple, actually. So we have a velocity vector, right? This is the velocity that is being fed by the loiter controller. And we try and detect, we have these obstacles coming in from the proximity library. And we try and detect, how much of what component of this velocity vector is towards this obstacle. We basically project this vector onto this obstacle vector. And this is the drone right here. Then if we find out that it is getting quite close to this obstacle right here, we try to shorten this vector towards the obstacle. So the projection of this vector towards this obstacle, we try to shorten it, and then we add it back into the velocity vector, and the result is something like this, right? So if you were going straight ahead, instead of going straight ahead, now you're going to have the tendency to slightly bend to the left or the right. The very obvious problem with this method is that number one, if you are directly, if you're perpendicular to the obstacle, the projection is also going to be in the same line. So you just end up shortening your velocity vector and not actually, changing directions. So if you're, going straight to a wall, you're not going to go left or right. You're just going to stop right in the middle. But if that wall is, slightly tilted, or if the vehicle's direction is slightly, oblique towards the wall, then we're going to have a smooth sliding feature that we support. And the biggest problem that we had in simple avoidance till 2020 was that it can stop in front of the vehicle. It can stop in front of the obstacle. It can slide around the obstacle. But if the obstacle was to come closer to the vehicle will not go back. So we didn't have an active avoidance feature per se. We just had a detect and stop feature. But now in 2021, we can actually maintain a set distance from the obstacles. So this was a feature that I developed back in my GSOC times. It was one of the highlights of my work. And what we do is that we could have obstacles. It's not as easy as it seems, because we can have obstacles from all directions. So we can have obstacles from the front, we can have obstacles from the back, and if we are backing up, we have to make sure that we don't back into an obstacle. So this has I won't get into details of it, but this has a slightly it just calculates a vector which is free from all the obstacles, and it bang in the opposite direction of all the obstacles. And so this was a very interesting simulation scenario that I developed using Morse. So Morse Simulator is an excellent platform to test avoidance related stuff, because we have a good support for it. And unfortunately, Morse is now dead, and it's not being developed by it's not being actively developed. But just using the last Morse version is fantastic. So you'll see in a minute. So I call this simulation the choke room. And I love it because we have walls from all sides that are diverging into the copter. And you'll see just in a minute that, so this is in loiter mode, right, with simple avoidance, and walls are approaching from all directions. And you'll see how we back away. And so this is the new feature that we're releasing in Copter 4.1. And if a user was to do this in Copter 4.0, it's just going to collide into the walls. It's going to stop right in front of it, but then when the walls come closer, it's going to collide. Similarly, just approach it from any direction, anywhere, and your copter is safe. It's going to try and maintain, as much of a margin as possible. So that's about, backing away, and the biggest feature of simple avoidance probably that we have. Apart from that, simple avoidance is now smoother and safer. So, when I started experimenting with avoidance, and a lot of people on the discussion forums as well, actually, they used to report that the vehicle is very aggressive, the vehicle is twitchy, and which is not a good thing, right? Because if you're trusting your vehicle to not collide into something, especially beyond visual range flights or FPV flights, you don't want vehicle to be twitching when you're avoiding obstacles. That's just eyesore. And so I investigated the reason of why this was happening. And this graph actually pretty much explains the reason of those twitches. So we have the input velocity, and then which is coming from loiter, and we have an output velocity which is coming from the avoidance libraries. And what happens is that the difference between the input and the output velocity, which is basically the acceleration demanded by the avoidance libraries, it reached hundreds of millisecond second, which meters second, which was just crazy, right? I mean, vehicle can't accelerate that much. And so what I did was we have this new feature called we have this new parameter which can actually limit this acceleration to. So this is right now limited to 2 meters per second squared. And this is what the avoidance code actually demanded at first. So just to give a demonstration of what used to happen and what happens now with this new bit feature. If the vehicle was traveling fast, it used to react this aggressively, and you'll see that it starts. So this is the this is the obstacle right here, which is this will never happen in real flight. I hope that there's an obstacle 10 centimeters away from the vehicle, but you'll see that the vehicle is just swinging around, and it's not a controlled backing away. It's just going crazy, as you can see. And that no one's going to be trusting their vehicle with avoidance if this is what it's doing, right? So to fix this, as I said before, we have this acceleration limitation code, and yeah, so just have a look at what it does now. So it's flying, quite fast, and my hand comes, and there it is. And you'll see the velocity being, gradually decrease instead of, having a sharp decline in it. And the acceleration is very much limited. And just once more, if you see the vehicle going straight forward, and my hand comes in between, it stops gradually and it goes back. So yeah, this makes the flight much smoother. And if you see on the top corner, this was the expected acceleration, and the expected acceleration, this is the kind of stuff that we were demanding out of the vehicle. 500,000. I mean, that's just crazy. We can't do that. So all of this is now being limited, and the result can be seen. Right. And one of the other biggest changes to simple avoidance is that it is now 3D, because we have 3D data that is coming from proximity sensors. So, and we have the ability to store 3D data. So of course, you're going to see a lot of this now 3D, because that's pretty much what I've been doing since the past year, converting everything to 3D. Yeah, this particular test is with a D455, which is stereo depth camera that I introduced a few slides back. And this is a test of it flying. And I also want to take a moment here to thank my main sponsors for this work, which was Harris Aerial. They provided all the funds and all the equipment, all the funds that are needed for the equipment. So it would not have been possible without them. So thanks to Harris Aerial. Right. So just to explain you what is going on here, we have this FPV view of the camera. So this is a tripod on the left with a surface mounted camera. On the right, you see a FPV view. On top of that RGB FPV view is a filtered depth camera view. So this is filtered. Okay, this is not the raw depth that is coming from the camera. The raw depth visualization that is coming from the camera is on the left, in the top left. So again, crazy on how much data we are processing and how much data we have. Right. So you'll see the vehicle approaches me, and just have a look. So as soon as I start approaching the vehicle, it moves back, and so that's the minimum it can do. But what's more interesting to see is that if I approach it from below, then it's going to actually climb up. So it's very, very slight now, but you can see that the vehicle is actually climbing up instead of going back, because that's where this was a user commanded movement, by the way. And yeah, just in a moment, you'll see that the vehicle will actually attempt to climb up instead of going back. And this is also a recent change that we have done. Yeah. So as you can see, it's pretty smooth, and with all this data, it's a much safer flight now, and it's all working great. So right. So that was just with one camera, right? And that was just with that limited amount of data that we are receiving from one camera. But now, with all the work that has been put into by Peter Barker, by myself, and by Randy, we can actually have multiple depth cameras that are attached to the vehicle, and to have like a almost 360-degree view of the vehicle. And again, all this work was sponsored by Harris Aerial and QPilot. QPilot actually, donated me the vehicle required for, because all these cameras are heavy, all the companion computers are heavy, and I needed a much bigger vehicle. So QPilot was happy in providing me that vehicle, and all this would not have been possible without them. So thanks to QPilot. Right. So this is the setup that I've used for this interesting use case. So we have two cameras. If you notice, there is one camera at the front. This is the D455. And there's one camera at the back, which is the D435i. And we have the Jetson Nano. So the earlier versions that you had saw, that they were using the Intel upsquared. But since then, I have you started using Jetson Nano. And this is a Hexoon TD650 frame, and so it's a really interesting setup that I have here. And so just a wide, very, very wide view of what all is here. And so this is the front camera, the D455, and this is obstacle number one, the garden umbrella there. Obstacle number two is me right here, holding the stick. And on the back there is a D435i, and that's detecting obstacle number two. And so you just see the massive amount of data that we are processing, and that is being fed into the vehicle. And so the frames per second on this that I was getting out of the two cameras was a little below 10 frames per second, because the Jetson Nano can't really keep up with, it's not good with multi-camera support. If you had just one camera, you'll get 15-16 frames per second, but which is sufficient. But with two cameras, it was lagging. I think if I upgrade to a better Jetson computer, like a more expensive one, like the TX2 perhaps, then it's going to be slightly better. But for a demonstration, this works. So you'll see in a moment that I approach the vehicle from behind, and the copter reacts to it, right? And it stops right in front of the obstacle, the other obstacle. And so no matter what I do, it's not going to collide into it. It's going to go left, right, but it's not going to collide into it. So I'll just let the video play, and just tell you what exactly is happening. You can go up, you can go down, which was earlier not possible with 2D lidars, right? But it's not going to, yeah. So obstacles on both sides, but now you're going to see that it's going to attempt to go to left instead of going straight. So yeah, that is just amazing ability, right? That the vehicle will refuse to collide into any obstacle no matter what you do. And the avoidance, another thing to notice is that avoidance is mostly smooth. It's not twitching around. It's not reacting aggressively either. So on most parts, it should help the users avoid obstacles and not really be a gimmicky feature. Another just a cool demo in the same video is, just a second. Right. So right now you'll see that, just this one camera set up on the left and the copter flying. So I'm pushing on the sticks. If you see, I'm pushing as far possible as I can. And this is loiter mode. And the vehicle is just still there. It's just standing steady. It's not doing anything. And which is amazing, right? You can go left, you can go right, but it will not let you go forward. And you can approach it from any direction, up or down, as long as it's in the camera's frame. It's not going to let you collide into it. So that's just, I mean, it's just self-explanatory how this can be used, right? So that was it about simple avoidance and how much we have upgraded it in this year. And we have a couple of tiny features as well that I've not mentioned, but so we have this huge issue of detecting ground as obstacle, and I already told you that in proximity avoidance, sorry, in the proximity library section. But so to counter that problem, we also have this new parameter which you can set up, which basically says that do you want a minimum altitude before avoidance is switched on? And if you're below that altitude, then avoidance is automatically turned off, and so you don't react to the ground. And another thing that is to do is to make slide more slidey. To it does slide, but we want to make it a little bit more than that. The slide should be more obvious. And obviously, we can't say that it is 100% reliable or 100% smooth. Those improvements will keep on going forward as time progresses. A real cool video of so I'm working a lot on ground detection. So a really cool video of how we can do it outside of ArduPilot, how we can do it at the companion computer level. So yeah, so again, this depth visualization and this RGB camera view. But this time, if you see on the depth view, we have these tiny circles, and these tiny circles is actually land. It's the land that is detected. So if you see when the video unfreezes, yeah. So it's tracking the land pretty well, right? And I'm flying quite low, but if you notice, there are no red. So there's this red distances here, as I told you before, but there are no red distances here because it is not detecting any valid distances, and that is because we have land here. So yeah, so you can do all sorts of crazy. And this algorithm, by the way, it's a very simple algorithm called ransack. Many of you might know. I can, if I start explaining the algorithm, we'll go over time. So I'll skip the algorithm description. But yeah, so you see how low the vehicle is flying right now. It's barely a meter above the ground, but the land is being detected, and it's not reporting any obstacle. So that's just a great thing to have. And this feature does not exist yet in the scripts that we provide, but I'm hopeful that in the very near future I'm able to have this feature as well. And so when an obstacle does come in between, and there is land, so that's the obstacle, you'll see that the obstacle is being detected and the black dots move away. So that's also a good handy feature to have. And this makes it like super reliable. So you have ground detection filters here, you have ground detection filters in proximity library, you have ground detection filters in avoidance, and all three of them together, you can be almost sure that ground is not going to play any role in low altitude flying. So yeah, that was it about simple avoidance and manual mode avoidance. The rest of the presentation is going to be about obstacle of path planning and autonomous in autonomous mode. So any questions so far? Right. So I'm audible, right? My mic is working fine.
Yes, it's just
Yeah,
it's quite incredible. I mean, it's sure the question much so much as an observation. I remember Peter brought a vehicle running your code out to Spring Valley for us to try it. It was just to experience it directly was quite incredible. To watch it doing that avoidance, it was really quite stunning how well it works. And it's the sort of thing where I would love the conference to be in person and we actually have people experiencing just how well this stuff works. But yeah, very, very impressive. But should let you get on with the next section.
Right. Yeah, I'm going to go quickly because we're running out of time. So and yeah, just
we
one
go
last
a few
thing.
minutes over. Don't need to rush.
Yeah, thank you. So just one more thing before I wrap up this section. We are also actively working towards, and Peter Parker does more work in this, but on making really easy AP sync images out of this. So all you have to do is just connect everything and you're ready to go. So we are constantly working towards that. But this new development features, they take a little bit time to reach that section. So if you are a developer and you're interested in this, you can ping me anytime. I'll send you my scripts. You can try it out, and that'd be great. So next, moving on to the autonomous modes. So we have something called as the obstacle database. And this is needed for storing obstacles. So what this does is that it stores obstacle inside ArduPilot, inside the flight controller's memory, and that data is being constantly refreshed. And these obstacles, they are stored as earth frame vectors instead of body frame vectors. And the reason is obviously that we want to have some sort of memory with respect to obstacles. So for example, if you have a 1D rangefinder and it's yawing towards the right and it sees obstacles behind it, just because you have yawed a little bit does not mean that the obstacle is not there. So you want to have some sort of memory, right? So that's what the obstacle database does. And so it's a really, I love the implementation of how this was not implemented by me, it was implemented by someone else, but it's really great how it works. And the recent updates that we have brought about to obstacle database is that it is also 3D now. So it used to only store XY, but as like a vector from the origin, but now it stores XYZ. Which is really great, right? And we also have the ability to reject obstacles around home. And this was also, just a very simple feature to remove the ground that was being detected, right? Again, just adding on to that. So while we are taking off and landing, which is mostly around home, you can reject obstacles in the obstacle database. And you can choose to use this. You can, disable it with a parameter, up to you. So bendy ruler. So the obstacle databases, the obstacle database directly feeds into bendy ruler, and bendy ruler uses that those proximity data and for planning its path. So bendy ruler was actually algorithm that was the original work of Canberra UAV and Tridge and other people worked on it. It was first implemented for plane. It was not at all for rover and copter, but now it is only being used with copter and rover. And I think there are plans to have a Lua script for plane, but that has not yet been implemented. And so it is a relatively simple ray-based algorithm, and you can. So Randy also explained this, explain how this works in last year's conference. So you can have a look at that as well. But just to give you a little background, what it does is it does avoidance in 2 steps. Step number 1 is that it sees there is an obstacle in front, and so this red marker right here, this is the obstacle in front. It projects distance a little bit forward, and it sees, oh no, this is quite close to the obstacle, we can't go in this direction. So it turns a little bit to the left, 5 degrees to the left, and it sees, okay, no, we still don't have proper distance to, we don't have a set margin from the obstacle. So and then we turn right, and so so it just does this ping pong left right maneuvers, left right not maneuvers, but left right location projections till it figures out a position which is this green line here that is free from the obstacle. And at this point, we could stop this algorithm here and we could just go forward. But what this algorithm does is it does a step 2, which is that it does the same search, but in front of it from this already projected point, so that we are sure that once we reach this obstacle, once we reach this deviated point, there is no obstacle in front of it. I hope that was clear. So and this path, so we have two path planning libraries. We have Bendy Ruler and we have Dijkstra. This works with proximity sensors. So if a human starts walking towards it, or if a car starts running towards the vehicle is going to be able to avoid it. The same is not true for Dijkstra. So just a demonstration of how well this is working in 2021. So this is just a copter, going up, going to a zigzag sort of pattern, like back and forth pattern. And I usually have a slow moving vehicle so that if anything goes wrong, I'm able to control it. But it can be much faster than this. So now you'll see a wild obstacle appears out of nowhere, and as soon as the vehicle turns around and it sees the obstacle, it moves towards the left and it avoids it. And this is all purely Bendy Ruler, by the way. I'm not doing anything. I have the controller in hand, but it's not being used. It's just so that if it goes too much to the left or too much to the right and it collides with the where the sensor can't see, then we have a problem. So yeah, and it's just great how Bendy Ruler works. So that's about Bendy Ruler, and you can approach it from any direction, and it's just going to continue towards its path as soon as the obstacle is cleared. Right. So moving on. So what are the updates to Bendy Ruler in 2021? The updates are that obstacle detection is now 3D, but this does not imply that the algorithm is 3D. So the algorithm is very much 2D, and it only searches, in XY direction, or as I inbuilt. It's not a tough thing to do, but it's just that we have not gotten to it yet. And so with this feature right here, where the obstacle detection is 3D, you'll realize that when the vehicle is pitching downwards, and if it's rolling around, it might detect the ground, or it might detect an obstacle which is down below. But back in Copter 4.0, this was detected as something which is at the horizontal level. It wasn't detected as an obstacle down below. So now what we do is we multiply the obstacles with a rotation matrix, the attitude of the flight. And so the difference that it makes is that in these this is again Morse, and this is this is Copter 4.0 on the left, and this is Copter 4.1 on the right. And you'll see is that the vehicle keeps avoiding random obstacles which were actually down below and not in front of it. But the vehicle on the right is traveling smoothly. It has no problem at all. And this is a low altitude flight. There's like 2-3 meters. And just a second. So yeah, you'll see that this one has already reached waypoint 3, but this one's struggling to even cross waypoint 2. And you'll just realize that the copter in the end, because of such false, it not detecting those false obstacles, reaching the final state quite earlier than the Copter 4.0 version. So that's one update to Bendy Ruler. The other update is performance improvements. So the problem with Bendy Ruler was that it was it was too easy for it to change the directions. So if it is heading towards the left, and all of a sudden it finds that the path to the right is just a tiny bit better, like just minuscule bit better, it used to immediately switch over to it. There was no restriction on the how much path can be changed, which is not a good thing, right? So you'll see why it's not a good thing. So the vehicle is heading forward, and both of them react identically. The one on the left is again copter 4.0, and the one on the right is copter 4.1. And you'll see that the vehicle, they're both traveling, everything's fine till about this point. But all of a sudden, the one on the left, it started going towards the opposite direction. But the one on the right, it sticks to that pattern, and it doesn't deviate back. So, and you'll realize that this vehicle is now stuck. So if you were to do this in copter 4.0, it's just going left, right, and you won't be able to get out of it. But now you can, we hopefully have more resistance in path change, and that leads to just more robustness in this algorithm. So that's another change that we have bought in 2021. And so to do this, we have a couple of parameters actually, and I'm going to have a lot of documentation on, which is still left to do, but on how to do this. We also have a new bendy ruler type. So instead of going horizontally, for people who prefer the vehicle to go vertical, we can do that as well. So the vehicle is again flying back and forth, back and forth. This is a tiny, I hope you can see the tiny copter that is going back and forth. And right, so as soon as an obstacle appears, you'd see that the vehicle actually goes up instead of going left and right. So just in a second you'll see that. Yeah, so it climbs up, and it dodges the person, and it climbs down and resumes to its original path. So if you're in, say a farm or somewhere where there are low plants below you, or just if you prefer climbing up, then this is the feature to go with. And basic difference between this and the horizontal bendy ruler is that it just searches for free path vertically instead of horizontally. That's the only difference. Yeah, so that was it about bendy ruler and what are the updates to bendy ruler. Now moving on to the other type of path planner, which is Dijkstra. So I'm not gonna explain how Dijkstra works, and I think Randy did it in his last conference. But just to give you a little idea, Dijkstra is a very very famous algorithm that is taught to almost all math majors, all CS computer science majors, and if we have a set of nodes, it helps us calculate the least, the shortest distance path through them. It's a graph-based algorithm, and it's just very famous. You can read about it on Wikipedia. You have multiple YouTube videos, and so we have that as well in ArduPilot. And but this does not work with proximity sensors, and I'll tell you why in a while. So the way this works is that we have this fence. This black line is a fence, and it marks these safe. It creates these nodes, these red dots, these safe nodes, and it plans a path through them. So this is the shortest distance through the nodes, and that's basically how Dijkstra works. Yeah, just a second. Yeah, a new addition to, so as I said, that Dijkstra does not really have the ability to detect proximity-based obstacles. But the reason is that Dijkstra takes a long time to process, and even for a small obstacle, usually the tendency is that the obstacle database, it stores 50, 60 different points inside it, and so we'll have 50, 60 different nodes. And then this keeps changing, so the Dijkstra's algorithm will have to rerun again and again and again, and that's just something that most computers can't keep up with. So that's the reason why Dijkstra does not really have proximity sensor detection. So to still use Dijkstra's and to have the bendy ruler capabilities, we have come up with a bendy ruler and Dijkstra fusion. So we use, so this is sort of like a ROS way to a robotic operating system way to do this. So we have Dijkstra's as a global planner, which basically at the start of the mission, what it does is that it plans a path that this is the general direction that we're going to go towards. And if we have a few obstacles in between, that is, bendy ruler job. We're going to switch over to bendy ruler. It's going to take care of all these obstacles. And as soon as all the physical obstacles, the proximity based obstacles are done, it's going to switch over back to Dijkstra's navigation. So now users don't have to choose, do we want bendy ruler or do we want Dijkstra? We want Dijkstra, but we can't use, it doesn't have proximity based avoidance. So now choose this, which is going to be available in Copter 4.1 and Rover 4.1. And just a simple demonstration on how it is much easier to demonstrate this on simulation rather than real flight video. So I have this, the vehicle is in guided mode, and the vehicle is down all the way here, and I have asked it to go here. So the green line here is the fence, right? And there are proximity obstacles as well. So it has decided to go around the fence. That's all Dijkstra. And on the top also you'll see Dijkstra is being printed, because that's the OA type that we are using right now. And as soon as the vehicle approaches the obstacle, it switches over to bendy ruler, and now it's going to so it's deviated from the path, as you'll see on the bottom right corner, and it's the only thing that is doing right now is avoiding this obstacle right here. And as soon as this obstacle is avoided, it's going to switch back to Dijkstra. So in a second, you'll see the map right here. And right there, you'll see that the path is all of a sudden, the Dijkstra's path is calculated, and it has switched back to Dijkstra's maneuver. And it's just going, now it's the shortest path again. So you're covered in all ways. So this is again the newest path planner feature that we have. And what's left to do. So again, the obstacle detection is 3D, but bendy ruler itself is not 3D. It's very much 2D. So do that. We can integrate simple avoidance in our autonomous modes as well. So that PR exists for this. I've done it. It just needs a little bit more testing. So most likely 4.1 is going to have this in next couple of weeks. Spline navigation, to the best of my knowledge, does not work with the path planning algorithms, unless that has changed in S-curves. I'm not aware of. But up until at least last week, spline navigation, if you were to use spline navigation, it's just going to collide into the obstacle. So that's something that we need to do. And yeah, Dijkstra does not support proximity avoidance, but I explained, that's probably for the best. So this is the very last part of my, last couple of slides, and I'm almost done. Sorry for taking more time than I was allotted with. So this is just for those simulation geeks that love simulations. And as I said before, simulation is kind of tough in this area. And back when I was a noob and I did not know how all of this works, I used to just test everything on flight. And I have had, scripts crashing down and that causing, the blades to cut into my hand and stuff like that. So several body parts have been injured in the process. I'm not lying. And I'm sure, same is the case with everyone else. So we have two excellent simulators that are really easy to use. Thanks to people like Tridge and Rajat and, all the people who have worked on AirSim and, Morse. These are excellent platforms. That you can use in combination to settle to test everything before you take flight. I hope you remember, the land detection code that the ransack algorithm that I showed to you a while back. Before I tested it on flight, I actually coded the same thing on AirSim. So this is how it looks on AirSim, right? This is the depth view. It's the exact same. It's the D435i simulated in AirSim, and this is the the RGB view. This is the depth camera view. And you'll see that the land is being detected with those black arrows, and I didn't even need to change any code. I just copied it as it is from from this to the RealSense cameras. It was that easy for me. I didn't need to change anything. So you'll see how well these simulators actually work and how incredible it is to use them. You can have all these blocks and so you can take it to crazy things like flying just half a meter above the ground and see if your algorithm is robust enough to detect obstacles there. And so as you realize that my algorithm right now is working quite nice, and as soon as the obstacle approaches, it's going to detect it and it's going to stop. So that's how incredible AirSim is, and I'm going to have a lot more documentation on how to set up this sort of stuff with AirSim. And if you're someone who wants to do multi-camera simulation, multi-depth camera simulation with AirSim, so this is the one on the left is a forward-facing depth camera. The one on the right is a backward-facing depth camera, and one on the top is a bottom-facing depth camera. And so you can do, and just see the amount of details that AirSim gives us. It's as good as testing physically. And so it's again divided into those 3x3 grid that I was talking about earlier. And just see how detailed the simulators really are. And when it starts approaching, you can see the trees, and you can do any sort of ML AI stuff that you want to do, or any statistical analysis you want to do, you can do it right here. You don't need to take your copter out anymore. And if you want to, so this is again something that I really want to work on the future, that have the camera pointed downwards and be able to detect terrain much before the copter is on top of it, right? So right now we have a downward facing rangefinder, and when the vehicle is on top of that terrain, that's when we actually figure out where the if you have to climb or descend. But we can actually plan for it in much more future if you use these cameras. So yeah, so as you'll see, if I pause it right here, this is the downward facing, this is how the trees look from the top, and this is how the trees look from the forward. And it's just crazy on how much how you don't even need to get out of your seat anymore, and how you can just use these simulators. So yeah, and then there's more, which I've already showed you a few videos of, with the joke room and stuff like that. So that was it regarding my presentation, and hopefully you guys had had fun looking at all the experiments that I did. And yeah, stay safe and fly safer. And apart from that, I just want to give a shout out to all the people that I've worked with, Randy, Peter, who have been really mentoring me. It's just been a year. It's just been a year since I've been with involved with you guys, and it's just been transforming on how much I've learned. So thank you, and that's it from my side.
Fantastic. That was absolutely brilliant, Rishabh. Really enjoyable. And it's incredible the progress that's been made over the last year on object avoidance, and it's great to see that the simulation systems being used in such a marvelous way. So really gladdens my heart to see all this stuff coming together so well with such sophisticated capabilities. So are there any questions off the floor?
Hey, Tridge, this is Bill.
Yeah, g'day, Bill.
Hey, Rishabh, this is great work. I really loved watching your presentation, and really great capabilities that have been brought to the to ArduPilot. But the question for you is, what hardware do we need? I mean, so the depth cameras, it seemed like you had some sort of a companion computer or something like that doing calculations. Right. Or so I guess describe real briefly, kind of with depth camera, what do you need? And then with, like, I guess there's the 3D, or not 3D, but basically the rangefinders, I guess. Which one of those require companion computers? Right.
So all the yeah, thanks for this question. And so the really easy answer to this is that all the sensors that we support directly in Copter. So those are the lightware sensors, or the rangefinders. Those are all directly connected to the flight controller, and so you don't really need any companion computer with that. You'll get this exact same, all the exact same output without any need of companion computers. You just need to set the right parameters and you're good to go. It's that easy. But with these cameras, with these 3D cameras, so it is important to know that all of the calculations actually happen inside the vehicle, inside the flight controller. And the only usage of the companion computer is to connect to the cameras, extract the depth image, and just basically divide it into a 3x3 grid, and in whatever way, and pack it into a XYZ obstacle and send it as a mavling message. So that's the only use of the companion board. But all the calculations, all the avoidance, all the 3D spheres stuff that I was showing you before, everything's done on board.
Great, thank you.
Anything, if I can answer any other questions.
Yeah, I've got, well, first up, on behalf of all the other developers, we all hope you healed up quickly as you were developing everything. And how have you gone with, you look like you've got a lot of USB 3 sort of floating around there. How much trouble have you had sort of, dealing with interference and that sort of stuff? And is there a way of sort of doing it without using, those painful things?
As you said, the multi-camera support, when you have more than one camera, it's a pain in the head to have all those cables and all those USB 3, and these, by the way, require USB 3.0 ports. So I have only tested with 2 cameras because I only have 2 cameras, and it's not been a issue so far. But as I read on the forums, and so I spent like hours scrolling through forums, figuring out what the problems I have and if other people have it. So what people tell me is that beyond, at least on the Jetson Nano, so if you have a high-powered laptop like I use, it's not going to be an issue. You can use a USB extension hub, and you can connect as many cameras, like 5, 6, 8. I've seen people use 8 cameras at a time, and it's not really an issue. But with a low-powered flight controller, a low-powered companion board like the Jetson Nano, anything more than like 2 cameras, you're not only going to reach the limit of how, if you can on the CPU limits, but you're also going to reach the bandwidth limit of the USB ports. So anything more than 2 or 3 cameras on the Jetson Nano is not advisable at the moment. But if for high-powered companion boards, you can easily go to 4. A lot of people have done 4. But there is no way we can circumvent that at the moment. You can have multiple companion boards if you want, but that's not a solution, right? So sorry, no solution for that.
Is there any opportunity to work with work with the cameras themselves to output just the data we need for the autopilot?
So I have asked Intel about this in one of the forums, and they said that this is something that they want to do, which will be really interesting. So you can have like just a tiny camera, and a few cameras actually do this. The Intel the depth cameras that I have used don't do this, but that is very much a possibility in the future. Companies are working on it, but we don't have a product yet that does this. And when that happens, we won't really need any companion computer, right? We just need Mavling messages being transformed from the camera directly to the vehicle, and all works well.
Thanks, Matt. Great work.
Thank you. Is there anything else I can answer?
There's one from YouTube, mate, just from Scott Arrow. If the obstacle is suddenly removed, do you get full stick input immediately, or does the controller slowly add in all the stick input?
Yeah, this is a very good question. So right now, this is a problem with Copter, that if the obstacle is removed all of a second, it does have the tendency to give a bit of a jerky reaction. So while the obstacle comes in front of it is not an issue, but if the obstacle is removed, it is a slight issue. But this is something that I'm working on, and this is something that I noticed just past week. So I'm sure that in the next month or so, we're going to have a solution for this as well. But it is a problem right now.
Cool.
All right, fantastic. So no further questions? Randy?
No, I was just saying, just really great work, and working over the last year or a little bit more with Rishabh. What I really always appreciate is just the level of testing that he does. So there's no point in having a obstacle avoidance system that isn't reliable, but he just puts so much effort into the testing to make sure that it really works. It's
Randy,
a real pleasure.
Randy and I have kind of been lucky enough to see this sort of presentation on kind of a weekly basis for quite some time, which has been absolutely fantastic.
Thank you. Thank you so much, guys. And it would obviously not be possible with without the mentors like I've gotten. And just last line that I just hope that avoidance is not a gimmicky feature anymore, and it is something that we use compulsorily in all vehicles, and people actually start testing it and start realizing that it is reliable, and they can use this in their everyday vehicles as a fail-safe feature, and not as something that they shoot a video and then they turn it off. So I'd love to hear reviews of people, of developer team members who flash 4.1 and start testing them. And if there are any, we have changed so much, like we have added so many new features that we're bound to have bugs, but I'm going to be all on top of it and hopefully fix it as soon as possible.
Fantastic. Thank you so much. All right. Well, that ends the evening's presentation for the second session of the 2021 Dev Conference. And thank you very much for the two presentations we had this evening. So we're back tomorrow morning, Canberra time, which is probably for many of you going to, if you're in Europe, will be the middle of the night. My apologies for that. So we're starting off bright and early with at 9 o'clock in the morning, Canberra time, with Tom Pittenger giving an AP Perif update, followed by Julio Mendoza about ArduPilot in Latin American research, and then documentation update and the ANU visual odometry system. Then finally, the blimp support from Michelle. So really looking forward to those talks in the morning. And so thank you all for attending this evening, and thank you everyone who joined us via the live stream on YouTube. And so wish you all a great evening and look forward to talking to you all in the morning. Good night, everyone.
Catch you later.
Thanks, Tridge. Good night.
Hey, everybody. Good night.
Cheers.
Bye-bye.